Okay, in this movie clip, I'm going to tell you some great details how to understand and how the PN junctions are working with a small signal. Uh, Previously, when we are studying the forward bias and reverse bias characteristic, I mean the current voltage characteristic under forward and reverse bias, how the PN junction can flow its own current. Well, short in summary, under forward bias, PN diode can flow a bunch of current. However, under reverse bias, the current is almost shut down. So in this lecture note, what if the given or externally applied bias includes DC plus AC signal? Then how to work? How for PN junction diode to work with or for a given small signal voltage? Since the small signal itself is fluctuating, I mean, it's a time varying signal. As you know, the DC voltage itself is invariant to time. So time invariant signal, which is the DC voltage, is you know kind of sort of a easy to understand and easy to handle it. However, the time varying signal, such as a small signal or AC signal with its own frequency, it sounds tricky. How to deal with it for PN junction diode? So herein, uh, for a given PN junction diode, we are going to apply externally DC bias plus small signal. So suppose that this small signal has a single frequency value. So omega means a radian frequency, which is equal to 2 pi times frequency. Okay, so since this small signal has its own single frequency, it would be more or less easier to understand how it works. Okay, and after understanding the small signal model, after developing this small signal model, we are going to move forward to go over the details on transient response. So turn off or turn on uh, analysis is to be announced and to be discussed. So small signal model, all the details can be found in chapter 7, and transient response can be found in chapter 8. Okay, so take your own time to read all the sentences in chapters 7 and 8. Okay, so herein, let's take a look at how to draw and how to develop the small signal equivalent circuit for PN junction diode. So simply speaking, what is the PN junction diode? Well, the p-type material plus or in contact physically with anti-material. It's a very simple device structure. However, for a given small signal, AC signal, how does the PN junction diode respond? So to think or to develop your own thinking for a given externally applied small signal, always come up with what kind of components, capacitive components of this device that you are interested in. So in this specific case, PN junction diode has its own capacitance component. What are they? As I have taught you last movie clip, under forward bias, the holes can be injected from P to N side. So those holes would be accumulated in the N side quasi-neutral region because of the DC bias. Okay, what about the electrons? The electrons are injected from the N side into the P side quasi-neutral regions, and those injected electrons are accumulated and stored in the P side quasi-neutral region because of what? With the help of DC bias. Then the question is how to deliver the small signal voltage. toward the PN junction diode. Most likely, small signal, as the name itself has indicated, small signal is super small. So it would be very vulnerable to the noise, externally coming, noise. So even it's hard to separate the small signal itself from the noise or white noise. Therefore, the small signal that we would like to deliver to the receiver communication system, that small signal should always be combined with or loaded up to the DC bias. And that DC bias, in some sense, would play the role of, you know, biasing or designating the operating point of the PN junction diode. So herein, let me see. Let me go back to the first front cover, and here, this PN diode is now flowing or biased with DC plus AC. So if I draw the current voltage characteristic of this PN junction diode, then the voltage is VA. This is a DC. So all symbol is capital, and very small signal V sub A. All symbol is a lower capital. Um, Here VA. So if I draw the time axis in this direction, then maybe the signal would be this. Okay, and this amplitude of this small signal is corresponding to V sub A. And now this PN junction diode has been biased by DC and AC. So if I draw the IV characteristic of this PN junction diode, the working or operating point or quiescent point is this. So DC current I, and if I draw the time domain here in, the current would be up and down, right? Up, down like that. But take a look at the amplitude, which is amplified because the slope of this curve, IV characteristic, slope would be very correlated to the amplification or gain between input signal and output signal. Okay, so let me simply write down the same plot again here, IB. So this is a bias point, VA, DC voltage, and DC current, right? And on top of it, the voltage small signal has been added up to this DC bias. Correspondingly, the DC AC current is moving up and down. Okay, so I'd say this voltage is IDC here, which is denoted as simply capital I. Okay, so with that in mind, let's move on to this slide note, and the total current I is DC component plus small signal. Okay, then this IDC would be matched to which component, and this AC signal would be matched to which one. Think about this point first. Previously, I mentioned that the small signal itself is very closely associated with capacitive component of a certain device, in this case PN junction diode. So what kind of capacitive components does the PN junction diode have? Yeah, a few minutes ago I have mentioned that the stored holes and stored electrons in quasi-neutral regions because of the forward bias. And the total amount of charge stored in the quasi-neutral regions are well kept, even as long as the DC bias has been well biased. So since the small signal itself has been delivered with the help of DC bias, we should always see a DC bias, certain amount of DC bias, resulting in a certain amount of stored charge in the quasi-neutral regions. Therefore, we can draw the small signal equivalent circuit as follows. A certain amount of resistive component plus a capacitive component. But how come they are connected in parallel instead of in series? Why is that? Because this resistive component and capacitive components are biased by two terminals. I mean the anode and cathode electrode. PN diode has its own two terminals only, no other terminals, right? So this resistive component, I mean the series resistance component coming from the quasi-neutral regions and depletion layer itself would have its own unique resistance. And the stored charge, electrons and holes can be accumulated and stored within the PN junction diode, and those are fully governed by applied voltage between two terminals, right? Therefore, resistor capacitors are connected in parallel within the PN junction diode. Then we can come up with and build up this very simple small signal equivalent circuit. Okay, then now it's a kind of a circuit analysis lecture. So for this given node, voltage node, the input current I has been put in, and that input current should be divided into two branches. This is I1, I would say this is I2. So I is equal to I1 plus I2. But this I1 is using Ohm's law. You can simply estimate the current component I1. What is it? Yeah, I1 is all VA, right? But since 1 over R is identical to the conductance value G, okay, so I1 is equal to G times V sub A. So you can find it here. But this current component actually based on and obtained with the help of DC bias. Okay. And what about the I2? Yeah, I2 is now going through the capacitor. So based on your basic knowledge, capacitors, the how much charge can be extracted and stored uh, in a given capacitor is proportional to the how much voltage difference can be applied. So in this case, if I this delta Q divided by delta T, and this delta Q is divided by delta T, then current component I2 is proportional to the this component is matched to the current component because think about the unit. Q is charge, T is a second. So coulomb per second is identical to the amp, right? So I is proportional to the delta B over delta T. And this coefficient should be capacitance. So current I2 is capacitance times delta B over delta T. And if I'm using derivative formation, that should be I2 is equal C dV dt. Okay, and in this case, the voltage drop across the capacitor is matched to the VA, that is a small signal voltage. So instead of V, I'm going to use a VA. So you can find out that I2 is identical to C times dVA dt. Okay, we almost done. So herein, let me calculate and estimate the small signal conductance value. So G is defined as 1 over resistance, and how to get the resistance value under forward bias. So think about the current voltage characteristic again for a PN junction diode. So for given voltage, DC voltage, right, the DC current can be found. And now this R is defined as the slope of this tangent line, so that di over dA. So R is defined as, this slope is 1 over R, and R is defined as VA divided by I. Okay, so delta delta. So I mean the slope. So that the 1 over R is equal to, dVA over dI. And since now we would like to know the small signal conductance G, so G is 1 over R, and 1 over R is equal to this, so that it turned out that the G is equal to dI dVA. Okay, and now with the knowledge that you have gotten from the ideal diode analysis, what is the DC current voltage, DC current for a given DC, voltage across the PN junction diode? Think about the ideal diode equation. I is equal to I naught times exponential VA over what? Yeah, KT over Q, which is thermal voltage minus 1. And since once you know this equation, you can take a first derivative with respect to the VA. And this guy, the dVA. Then you're gonna get this. And since minus 1 is a very small number and constant with respect to VA, you can ignore it. And from here, you can see that Q over KT should be jumped out, and you're gonna get, let me see, yeah. From here, if you take a first derivative with respect to VA, Q over KT will be jumped out, and you're gonna get this equation. And take a look at this term again. This term is very similar and approximately equal to the, uh, you know, since this small signal conductance value has been obtained under forward bias. So in ideal diode equation, I naught exponential VA over KT over Q minus 1. Yeah, this value is very close to the exponential VA over KT over Q. Yeah, here the words that I would like to deliver to you is this minus 1 is almost negligible as long as forward bias is applied. Okay, because the current level itself is way higher than the saturation current I naught. Okay, so this second term I naught times exponential QVA over KT is almost equal to the DC current flow, even though I didn't include the minus 1 value, but it doesn't matter. Okay. So small signal conductance value G can be defined as I, which is the DC current flow, divided by KT over Q, which is the thermal voltage. So thermal voltage IDC. So going back to the small signal equivalent circuit, this resistance value itself can be obtained and determined which operating point or quiescent point Q has been defined and used. So for given PN junction diode, suppose that you'd like to apply, zero point 0.4 volt as a DC voltage, which means you are going to define your own small signal conductance. So depending on the quiescent point in IV characteristic, your small signal conductance can be predefined. In other words, you can design and you can designate the small signal conductance if necessary, as long if you can vary the DC bias point. Okay, and here in the small signal conductance G is defined as IDC over VT. VT is thermal voltage KT over Q. At room temperature, the value is 26 millivolt. Okay. So previously we have learned a small signal equivalent circuit for PN junction diode. And now is a good timing to review and look at how the charges are stored in a PN junction diode again. Let me draw the stored charge profile along x direction in PN diode. So this is a depletion layer. So Xn minus Xp can be used to designate the depletion layer edges on each side. And this y-axis indicates delta P sub n, access hole concentration in the inside, in the n side, okay? And here in the second y-axis indicates the access electron concentration in the p side as a function of x. So under fold bias, many holes can be injected into the n side and they're gonna be piled up, okay? And the area here indicates QP, the total charge is stored in the n side. And the electrons can be injected into the p side and they're gonna be piled up and accumulated in the p side quasi-neutral region. And that area indicates how much electrons can be stored in the p side. Okay. And since electron is negatively charged, so I'm going to put the minus sign here. So under forward bias, we can imagine and draw how the excess electrons and how the excess electrons and holes are accumulated and profiled out in quasi-neutral regions. Okay, and one more thing is my question is, what about the depletion region? Within the depletion layer, what kind of charges can be expected? Can you draw the charge density plot within the charge density rho coulomb per cubic centimeter? Uh, how much charges can be expected in each region? I mean, in the range of 0 to xn and 0 to minus xp. How much charge density can be expected? Well, definitely p side and n side are uniformly doped, homogeneously doped, so that the doping concentration Na or Nd is nothing to do with x. I mean, the Na and Nd is uniformly doped. So what is the charge density in the depletion layer? Yeah, this is the N side and this is the P side, right? N side is doped with the Nd, right? So Nd is a donor, so which going to be possibly ionized because it would like to donate its own fifth electron toward the silicon material. So positive charge Q times Nd, and since Nd is uniformly doped along the x direction, so we're gonna expect this plot. So that value indicates a plus. And this area indicates how much charge, positive charge, can be stored in the depletion layer on the N side. What about the P side? P side is, doped with acceptors, and acceptor is going to be negatively ionized because it would like to accept the free electrons, right? So that minus Q times Na here. So this area indicates the total amount of total negative charge to be found in the P side. All right. So with that in mind, we're going to study and we're going to classify two different types of capacitance in the PN junction diode. So the answer can be found here: depletion capacitance and the diffusion capacitance. So previously I mentioned that for a given small signal voltage, PN junction diode would, since PN junction diode itself has its own capacitance components, it would flow the AC current that was named as I sub 2 herein, right? So now I'd like to know and analyze what kind of capacitive components can be found in the PN diode. So for that purpose, we should first understand how the charges can be stored and how the charges can be found within the PN junction diode. For that purpose, we have reviewed how the charges can be stored in a PN junction diode. So in the last movie clip, under forward bias, these charge QPN minus QN can be found in the quasi-neutral regions. However, definitely within the depletion layer, the ionized impurities, ionized donors and acceptors can also be found so that the ionized dopant atoms would be the root cause for forming up the charged area in the depletion layer. However, under forward bias again, the Q and QP can also be found in the quasi-neutral region. So throughout the PN junction diode regime, in the depletion layer as well as in the quasi-neutral regions, there are a certain amount of stored charge. So we should take into account all those stored charges to understand and to build up the capacitive model. Okay. So, but under forward bias, you know, this area QP, QN, where is it? Yeah. Those two things, two stored charges can be varied depending on the DC bias. However, this QND and QNA itself is also dependent upon the forward bias or not. Actually, yes. Why is that? If you apply a strong forward bias, this whole depletion layer width would become narrow, so the total amount of charge, this area would become narrow. So under strong forward bias, this area would become narrow. However, what would be happened in this QN and QP? Under more strong forward bias, more holes would be injected into the N side so that this total amount of QP would be increased. So for the same DC bias, the charge stored in the quasi-neutral regions would show very opposite behavior against the charge stored in the depletion layer. So that is a good physical reason for us to classify two different capacitive components. Okay, so herein, due to the where's my pen? Yeah. Because of the variation of depletion charge, we can come up with and name it as depletion capacitance. And because of the variation of stored minority charge in the quasi-neutral regions, the capacitance component can be varied. So that is named as diffusion capacitance. So depletion capacitance comes from the ionized dopant atoms within the depletion layer, and so denoted as C junction or CJ, or some textbooks that is CDAP. Okay, and here CD, uh, capacitance, diffusion capacitance. Why diffusion word itself has been used? Because the stored minority carriers can be diffused out to flow the DC current. So for that purpose, um, diffusion capacitance can be formed together. So CJ, CD, two types of capacitance are closely associated within a PN junction diode. Okay, so now is a good time to analyze and develop an equation for CD as well as CJ. Okay, so in the next movie, click in the next move lecture note, the CJ can be found here. Well, CJ, depletion capacitance, this is very simple. Why is that? Since depletion layer itself doesn't have any free electrons and holes. In other words, it's a kind of insulator. And the quasi-neutral regions are full of holes in the p side, and these n-side quasi-neutral regions are full of electrons. So it's a kind of conductor. So two metal insulator metal. So MIM capacitor. But depending on the forward bias VA, the thickness of insulation layer would be varied. Therefore, the junction capacitance component or depletion capacitance component is very dependent of how much forward bias has been applied and how much charge can be found in the depletion layer. So this is quite similar to the MIM capacitor. So going back to the general physics class, the capacitance of a two parallel plate capacitor can be defined as dielectric constant of the insulating material. In this case, we are going to use a semiconductor material so that epsilon s has been used, and how wide and how big the cross-sectional area it is, right? The parallel plate itself, the area of the parallel plate, the bigger the parallel area is, the more and the higher the capacitance is, right? And the thickness wise, the thinner, the higher, right? So W is placed here. So junction capacitance can be defined as dielectric constant of a semiconductor times cross-sectional area of p-n junction diode divided by depletion width. So we all know this value, right? For a given forward bias, you can calculate, quantitatively estimate the depletion layer width W, right? So that's very easy, and you can do your own quantitative analysis for CJ, okay? Or in other textbook, people are saying that CDAP, depletion capacitance. Both are okay. Okay, so here one question is, what are these three ways to reduce CDAP? What are they? Very simple answer is the junction area should be reduced. Then CDAP would be reduced. Very simple idea. And another one is, instead of reverse forward bias, what about applying reverse bias across PN diode? Okay, so reverse bias can give us very wide depletion layer so that C depletion would be reduced significantly. In other words, under forward bias, CDAP C junction capacitance depletion capacitance is negligible. However, under reverse bias, the C junction CDAP is significant. And the last way to reduce CDAP is, you can control uh, you as long as you can increase the depletion layer width, you're going to obtain the reduced junction capacitance. So what is the way to widen out the depletion layer? Yes, you can reduce doping concentration, Na or Nd. I mean the lightly doped side. Lightly doped side. Reduce doping concentration in lightly doped side of European junction diode. Then you're for the same, DC bias, the depletion width would be widened out so that junction capacitance can be reduced significantly. Okay, let's go back to the previous slide again, and here I'd like to define the equation for diffusion capacitance, C sub D. So diffusion capacitance comes from what? Yeah, comes from the stored minority charges in the quasi-neutral regions. So this Q indicates, whole constant QP plus QN in the quasi-neutral regions. I mean, this guy here, QP, and this guy, QN. Okay, so how much electrons and holes are stored in the quasi-neutral regions would give us the value of diffusion capacitance, CD. So for given DC bias voltage, how much charge can be induced in the quasi-neutral region? That is the concept of diffusion capacitance. And then here the Q divided by tau P. Well, basically QP divided by tau P plus QN divided by tau N. That is more exact, but however, to make our life much easier, suppose that the PN diode is one-sided doped, so P plus N. Then many holes would be stored and accumulated in the N side, right? So this QP is much, much higher than QN. I mean, the less number of electrons would be injected in the P side, so total amount of electrons stored in P side is quite small, so we can ignore it, okay? And then a total charge throughout the PN diode on the forward bias would be almost identical to the how much holes can be injected in the N side, because this is P plus N junction diode. Okay, then this Q is equal to QP, and that is uh, that is, identical to the I over I times DC current, IDC current times hole's lifetime. So this hole, going back to the plot here again, once the hole has been injected here, hole is going to be diffused out. So this is the N side. So there are so many electrons. So how long those injected holes can be survived in the sea of electrons, right? So in that sense, on average, how much charge can be stored in the N side QP can be defined as IDC, the DC current component times the lifetime of holes. Okay, so here Q is equal to I times tau P. So plug in this value into the Q and you're gonna get this value. By the way, what is this? DIDVA. So going back this slide, yeah, there we go. DIDVA was small signal conductance, right? So here plug in the small signal conductance G value and you're gonna get that. And what was the G? Going back to the slide here, the small signal conductance G was IDC over thermal voltage. Okay, so plug in IDC over thermal voltage into G and you're gonna get this value. Okay, so diffusion capacitance is well defined which operating point you are using. Okay, so IDC is very the function of the DC voltage, right? And tau p is the kind of physical material physical parameter. It's depending on the defect concentration, depending on the effective mass of holes, and depending on the mobility stuff. So tau p, usually 1 nanosec to 1 millisec, but usually in silicon material, 1 microsecond is typical value. And kT over Q is 26 millivolt at room temperature. So most likely this IDC, most likely the DC bias point would give you the value of the diffusion capacitance. Okay, so in summary, the diffusion capacitance, the physical origin of the diffusion capacitance in PN junction diode comes from the stored minority carriers in the quasi-neutral regions. And that diffusion capacitance is very dependent of DC bias point. Okay, and as well as a minority carrier lifetime and thermal voltage, in other words, the temperature. What about the depletion capacitance, junction capacitance, CJ? Yeah, here, there we go. CJ can be obtained from the concept of two parallel plate MIM capacitor. So you can simply write down the equation for CJ. So the cross-sectional area of PN junction diode and the depletion width and the dielectric constant. Since we are using the silicon materials, so epsilon s, dielectric constant value would be kind of constant. We can never change it. And A is, kind of design parameter. So the wider the PN junction diode is, the higher the junction or depletion capacitance is. That's very straightforward, right? What about the W, depletion width? So this depletion width is a key knob and key parameter to determine the junction capacitance. So there were three different methods to reduce junction capacitance. So I have introduced three different engineering solutions. So please remember it. So now is the time to wrap up and to combine all the junction capacitance components for PN junction diode. Previously, we have drawn the simple RC circuit network as a small signal equivalent circuit for PN junction diode. And the resistance and small signal conductance value has been well derived. So depending on the operating point, the G and R can be found and determined. And this C, total PN junction capacitance, can have two its own components, junction capacitance and diffusion capacitance. So here, junction capacitance can be written with this equation, and the diffusion capacitance can also be found here. And so more or less, junction capacitance, diffusion capacitance is very dependent of DC biasing voltage, right? As well as temperature and the magnetic carrier lifetime. Okay, and again here, as I have briefly mentioned, that the C depletion or junction capacitance can can be very small and negligible under forward bias. However, under reverse bias, the junction capacitance is the main one. Junction capacitance dominates the whole total PN junction capacitance. And the opposite is correct. Under forward bias, the diffusion capacitance is main one. Okay, so moderate or very high forward bias, the diffusion capacitance value becomes significant, so you can ignore the junction capacitance. However, under small reverse bias and very negative bias, then the diffusion capacitance is meaningless. Why is that? Because holes can never be injected into the N side, and electrons can never be injected into the P side because this is under reverse bias. So CD, diffusion capacitance, is closely associated with the forward bias, and CDAP or CJ's junction capacitance is very closely associated with the reverse bias stuff. Okay, so remember, two junction capacitance can be observed throughout the PN junction diode. However, depending on a DC biasing point, which would be either forward bias or negative bias, reverse bias, the one of them, CD or CDAP, would become more dominant. Okay, and herein I would like to tell you some application. Uh, what kind of information and what kind of things can we obtain and can we monitor, uh, or what kind of things would be very valuable by measuring the junction capacitance of PN junction diode? So the answer can be found here. Previously, the junction capacitance is dominant one under reverse bias. Okay, so under reverse bias, so this VA value is very negative. Junction capacitance is defined as dielectric constant times A times divided by depletion width. So if I take a square for both sides and take a 1 over it, then you're gonna get this. And since we know the full equation for depletion width and plug in that equation into W, then you're gonna get this one. And notice that this N indicates a lightly doped side one. Okay. Then let's draw the C 1 over Cj square versus VA in the reverse bias regime here. For example, I have measured the junction capacitance value for 4 different reverse bias voltage. Then you're gonna get this data point. Then you're gonna draw the trend line or using extrapolation. Then you can estimate the slope of this extrapolated curve, as well as you're gonna get the x-intercept together. So going back to the equation above here, the x-intercept means when the VA is equal to built-in potential, the value 1 over CJ junction would become 0. Okay. So by measuring full data point, you're gonna uh, directly monitor the built-in potential. Furthermore, by monitoring the slope of this trend line, you're gonna get 2 times minus 1 divided by this. So take a look at this n. So from the slope, you can monitor the lightly doped side doping concentration. Okay, so you're gonna get two process parameters coming from the 1 over CJ square versus VA plot. Doping concentration in the lightly doped side one, as well as built-in potential. But again, Is there a way? My question is there a way to monitor the heavily doped side doping concentration? Actually, yes. This VBI is the equation for VBI is KT over Q times ln Ni square ND times Na. So suppose that P plus N PN diode. From this slope, you're gonna get the donor's concentration. And from the x-intercept, you're gonna get this built-in potential. You know this value. But since by plugging in the ND value, you're gonna get the Na value. Na is the doping concentration in the heavily doped cycle. So by knowing VBI and the lightly doped side doping concentration, you can also quantitatively estimate the heavily doped side doping concentration as well. Okay, so please have your own time to solve this example. Everything I have already explained it. So please take your own time and take a look at the summary slide as well. So see you in the next movie clip. Bye bye.